You know, if you've ever just stopped and watched an ant colony, it's pretty mesmerizing. They build these intricate nests, they find the best food, they defend their home, and they do it all with incredible precision. But here's the crazy part. There's nobody in charge, no general, no CEO, no master plan. So how on earth did they pull it off? Okay, let's get into it. Right, this is the big question, isn't it? How does all this coordinated action happen? Well, the secret isn't that any single ant is some kind of tiny genius. The answer is that the entire colony behaves like a single, intelligent being, what scientists call a superorganism. So to really get our heads around this idea of a superorganism, we have to start small. We have to look at the individual ant. And it turns out, an ant's whole life, its job, its body, its destiny, it all boils down to one single factor, and that is its size. It really all starts with what they eat. See, researchers figured out that a female ant's caste, basically its job in the colony, is set by how much nutrition it gets as a larva. A well-fed larva just grows bigger. And that difference in size isn't just about being stronger, it means becoming a totally different type of ant. And this right here shows you the two extremes of that spectrum. You've got your smaller worker ant, built for labor, no wings, smaller eyes, basically a lean, mean working machine. Then you'll have the much larger queen, who comes equipped with wings for her mating flight and a body that's all about one thing, reproduction. But these aren't just two different models. Think of them as two ends of a sliding scale, and it's size that determines where an ant lands. What's really cool is the order this happens in. An ant larva doesn't just wake up one day as a queen. Nope, it's a step-by-step process, all tied to how big it's getting. First, if it gets enough food, its reproductive system starts becoming more queen-like. Then, its sensory organs, its eyes, and those simple light sensors called ocelli start to develop. And finally, only if it grows large enough does it get its wings. It's this beautiful, gradual transformation. Okay, so size determines an ant's job. Great. But once you have all these different workers, how do they actually work together on something complex, like, say, finding dinner? Well, that all comes down to their amazing communication system. Their main tool for this is something called positive feedback. It works like this. A forager finds some food, and on its way back to the nest, it leaves a trail of chemicals called pheromones. Another ant smells it, follows it, finds the food, and lays down another layer of pheromones on its way back. The more ants that use the trail, the stronger it gets, which attracts even more ants. It's a self-reinforcing loop that can mobilize the whole colony in no time. But here's the catch with a system that's only built on positive feedback. It has a pretty serious flaw. What happens if the first food source they find isn't actually the best one? The colony can get trapped by its own success, stuck reinforcing a decision that's good but not great. And these graphs show that problem perfectly. So when the ants have unlimited access to two identical food sources, look what happens. One trail, that's the blue line, gets going first. And pretty soon, almost all the ants are on that trail. They're completely ignoring the other perfectly good option, the red line. The positive feedback is just so strong they get locked in. So how does a colony keep from getting stuck in these ruts? Well, nature, as it often does, has come up with a really elegant solution to balance out all that positive feedback. And that solution is negative feedback. In this case, it's just good old-fashioned crowding. Seriously, think about it like a busy checkout line at the grocery store. If one line is way too long, you're not going to wait, right? You're discouraged, and you go look for a shorter one. Ants do the exact same thing. Now look what happens when the food source is limited, which creates a crowd. In these graphs, the foragers split up almost evenly between the two sources. The red and blue lines are way closer together. That crowding acts as negative feedback. Ants that show up to the first spot and can't get in are forced to go exploring, and lo and behold, they find the second option. The system balances itself out. This is where you see the real genius of this system. On the left, with no crowding, the colony finds a food source, the blue line, and they stick with it. Even when a much, much better one shows up later, that's the red line, they're totally trapped. But look at the right. With crowding, that negative feedback forces them to explore. See how quickly they ditch the first source and switch their entire workforce over to the better one? That is swarm intelligence. So we've got individual roles based on size, and we have collective decisions that are made using these feedback loops. What's the big idea, the scientific principle that ties all of this together?
It's a concept called self-organization. It's this incredible idea that massive, complex patterns can emerge from nothing more than simple local interactions. No single ant has the big picture. Each one is just following a very simple set of rules. Like, is there a food trail here, or is this spot too crowded? But out of all those simple individual actions, this highly complex and incredibly smart colony behavior just emerges.
And this principle of self-organization leads to all sorts of amazing patterns. We already saw bifurcation. That's the fancy word for when the whole colony just flips a switch and moves to a new food source. But it also creates things like synchronized pulses of activity across the nest or waves of alarm signals that spread like wildfire. And it all happens from the bottom up. It's not designed, it's emergent.
This quote just sums it all up perfectly. The queen isn't a queen in the way we think of one. She's not giving orders. She's mostly an egg layer. The intelligence of the colony doesn't live inside any one ant. It's a property of the entire system, built from the simple interactions of thousands of individuals. And that leaves us with a really fascinating thought. As we try to design our own complex systems, everything from swarms of drones to city traffic grids and software networks, what can we learn from this elegant, leaderless, and unbelievably resilient system that evolution perfected millions of years ago in the humble ant colony?